Let's have a look at the assumptions of the OLS, of the linear regression, to make it valid, to make the estimates as accurate as possible. And these assumptions are called the Gauss Markov assumptions based on these two mathematicians who made them. So we have 6 of them. In this video we're gonna do 2, in the next video another 2, in the last one another 2, so that we can stay with short videos and focused. So model is linear in parameters. What does that mean? That means that the relationship between the independent variable and the dependent variable has to be linear. So the most typical one is y equals to alpha plus beta times x plus a certain error. Now we can see that beta, it has a linear effect of x on y. Now one thing I want to clear is that we can also have a linear effect of x on y, although the independent variable x can be quadratic. For instance, y is equal to, let's say, alpha plus beta times x squared plus a specific error term. Although we have a quadratic term, this is considered our independent variable as a whole, but the effect, the actual beta, the actual slope is still linear. So the model is still linear in parameters, and that's the key word here. It's linear in parameters, but not necessarily linear in the variables, because the variables, as we can see in this case, we can have a quadratic variable, a quadratic effect of x. We could have had ln of x, so a logarithmic effect, but the slope itself has to be linear. Alpha itself has to be just a constant, not alpha times beta, for instance, because in that case it's not going to be linear anymore. It's going to be a function of alpha taken with beta together. But anyway, that's becoming unnecessary. Keep in mind that the parameters, and the parameters we're referring to, alpha and beta, have to be linear. Now, when we speak about a random sample as a criteria for having a valid regression, a valid OLS, what does that mean? Well, that means that the regression that we're drawing must come from a random sample, because we want to represent the population. So we must take a random sample in order to represent the actual population. And let's stick to our example. Let's give a practical example so we know what we're doing. Let's get some more space. Let me zoom out. Let's say we use our model by estimating wages on education. So wage of a certain individual is equal to a constant plus beta times the years of education of that individual, and a specific factor for predicting that wage of that individual. Now, if we take only the sample from a certain country, and those people from that country went to private schools, is that going to represent our population? Well, it's not, because people who can afford private schools are the minority. They're the elite. And of course, private school, better education, probably better opportunities overall. But if we take a random sample, if we take people from, private schools, if we take people from public schools, if we take people from poor areas, if we take people from rich areas, if we take people overall from several countries in Europe, several countries in America, several countries in Asia, in that case we can have a better picture of what would be the average effect of education on wage for the entire world, for instance. But usually we don't go so far as to predict for the entire world. Most likely we're going to predict for a specific country. Let's say the effect of education on wages in Sweden, for instance. Well, in that case, we will go to Sweden and take random people from different areas in Sweden that afforded different types of education, and we can see what levels of wages they have, and based on that we can see the average effect of education on wage on people in Sweden. So Sweden is going to be our population, Sweden, and then our sample is going to have random people taken from the Swedish population. Hope this makes sense. In the next video we keep going.